Hi everyone, in this video we'll talk about the use of kernels in machine learning. We'll start with a little introduction and then we'll define the concept of kernel and show a bunch of examples. Let's start. The prerequisites for this video are a basic understanding of linear algebra, and only if you want to fully understand the example provided, you should be familiar with ridge regression. I'll leave some resources about these topics in the description. Traditionally, theory and algorithms of machine learning and statistics have been very well developed for the linear case. Real-world data analysis problems, on the other hand, often require nonlinear methods to detect the kind of dependencies that allow successful prediction of properties of interest. By using a positive definite kernel, one can sometimes have the best of both worlds. The kernel corresponds to a dot product in a usually high-dimensionally, possibly infinite, feature space. In this space, our estimation methods are linear, but as long as we can formulate everything in terms of kernel evaluations, we never explicitly have to compute in the high-dimensional feature space. This is called the kernel trick. Suppose we have a mapping phi from Rd to Rm that brings our vectors into some feature space Rm. Then the dot product of x and y in this space is just a dot product of phi of x and phi of y. A kernel is a function k that corresponds to this dot product. Why is this useful? Kernels give a way to compute dot products in some feature space without even knowing what this space is and what is phi. For example, consider a simple polynomial kernel k in function of x and y, which is equal to 1 plus x transpose y squared, with x and y in R squared. This doesn't seem to correspond to any mapping function phi, it's just a function that returns a real number. Assuming that x and y are vectors with their coordinates x1, x2, and y1 and y2, let's expand this expression. Note that this is nothing else but a dot product between two vectors, phi of x and phi of y. So the kernel k computes a dot product in a 6-dimensional space without explicitly visiting this space. Another example is the Gaussian kernel k. If we tail or expand this function, we'll see that it corresponds to an infinite-dimensional codomain of phi. Instead, the simplest kernel is the linear kernel, which corresponds to an identity mapping in the feature space. Moreover, the kernel is a symmetric function of its arguments. Many linear models for regression and classification can be reformulated in terms of dual representation, in which the kernel function arises naturally. For example, if we consider a linear ridge regression model, we know that we obtain the best parameters by minimizing the regularized sum and squares error function. If you don't know what ridge regression is, check the description for some useful resources. Suppose we have the following loss function L sub w, where phi is the design matrix whose nth row is phi x sub n transposed. Remember that in the loss function, all the vectors are column vectors, and t is the target vector. Setting the gradient of the loss function with respect to w equal to 0, we obtain the following. Where A is an n-dimensional vector. We observe that the coefficients A sub n are functions of W. So, our definition of W is a function of W itself, which is surely weird. Just wait for it. We now define the gram matrix capital K, which is an m by n matrix. So, given n samples, the gram matrix is the matrix of all inner products. This will come in handy in a few seconds. If we substitute W equals phi transposed A into the loss function, we get the following loss function. Guess what? We can rewrite the loss function in terms of the gram matrix. Setting the gradient with respect to A equal to 0 and isolating A, we obtain where I sub n is the identity matrix of dimension n. Consider the k equals n by n and t equals n by 1, so A equals n by 1. We can make our prediction for a new input x by substituting back into our linear regression model, y of x, where k of x is an n-dimensional column vector with elements k sub n equals to k of x sub n x. The good thing is that instead of inverting an n by n matrix, we are inverting an n by n matrix. This allows us to work with very high or infinite dimensionality of x. But how can we build a valid kernel? We have mainly two ways to do it. By construction is the first way. We choose a feature space mapping phi of x and use it to find the corresponding kernel. Secondly, it is possible to test whether a function is a valid kernel without having to construct the basis function explicitly. The necessary and sufficient condition for a function k of x prime to be a kernel is that the gram matrix capital K is positive semi-definite for all possible choices of the set x sub n. It means that x transpose capital Kx is greater or equal to 0 for non-zero vectors x with real entries. Consequentially, we have Mercer's theorem. Any continuous, symmetric, positive semi-definite kernel function k, in function of x and y, can be expressed as a dot product in a high-dimensional space. New kernels can be constructed from simpler kernels as building blocks. Given valid kernels k1 and k2, the following new kernels will be valid. I hope you enjoyed this lesson and follow us on the optimal policy.